Welcome to Bedtime Astronomy. Explore the wonders of the cosmos with our soothing Bedtime Astronomy podcast. Each episode offers a gentle journey through the stars, planets, and beyond, perfect for unwinding after a long day. Let's travel through the mysteries of the universe as you drift off into a peaceful slumber under the night sky.
So, if you look up at the night sky tonight, the light hitting your eye is, well, it's basically a time machine.
Yeah, that's exactly what it is.
I mean, the glow from the Andromeda galaxy alone took like 2.5 million years to reach you. But it makes you wonder, what did the very first light in the universe actually look like?
Right, the absolute first starlight.
Exactly. And for decades, the universe's original stars were just these ghosts. Like, the math told us they had to exist, but telescopes saw absolutely nothing.
But today, in this deep dive, we are finally crossing that threshold from mathematical theory to concrete reality. We have actually found the first starlight.
It's honestly a monumental shift in astrophysics. Like, we are no longer just guessing about the conditions of the early cosmos based on, computer simulations.
Which is what we've been doing for years.
Right, now we're talking about the direct observation of a tiny, incredibly ancient cosmic object, something that existed just 400 million years after the Big Bang.
Wow, 400 million years. That sounds like a long time, but on a cosmic scale, it's nothing. To put that in perspective for you, if the universe's current 13.8 billion year lifespan was scaled down to a single calendar year, we're looking at something that happened in the first week of January.
Oh, wow.
Yeah, the universe was barely a toddler, and yet it was already constructing things of just unimaginable scale.
I want to focus on that phrase you used, direct observation, because for anyone who has just casually followed astronomy, the narrative has always been that the first generation of stars is fundamentally out of reach.
Yeah, that they burned out billions of years ago and we'd never see them.
Right. So the idea that we can now point a telescope at a patch of seemingly empty space and capture the actual light emitted by these primordial giants is staggering. So today we're going to explore this origin story. We'll break down how astronomers captured this ancient light, what these colossal structures were actually made of, and how they basically set the chemical stage for absolutely everything that exists today.
And to really appreciate the sheer scale of this breakthrough, we need to completely discard our modern understanding of what a star actually is.
Okay, let's unpack this. Discard it how?
Well, if you look at our sun, or Sirius, or Betelgeuse, you're looking at a highly evolved, chemically complex object. Astronomers categorize stars into different populations based on their chemical makeup.
Right, I've heard of this.
So our sun is a population I star. It's relatively young, and it's rich in heavier elements. If you look at the older stars orbiting in the outer halo of the Milky Way, those are population 2 stars. They have fewer heavy elements, but they still have some.
Which means there has to be a population 3, right?
There is, conceptually. Population 3 stars are the universe's absolute first generation of stars, and they operate under a completely different set of physical laws than anything burning in the sky today.
Because of what they're made of.
Exactly. It all comes down to the chemical inventory of the universe immediately following the Big Bang.
Let's dive into that inventory. Because when the universe first cooled enough for matter to form, it wasn't exactly a diverse chemical playground, was it?
Not at all. It was profoundly simple. Our modern sun has trace amounts of carbon, oxygen, nitrogen, iron.
All just churning inside of it.
Right. But population 3 stars had absolutely none of that. They formed from sprawling clouds of essentially pure hydrogen and helium.
So heavier elements like carbon and iron simply did not exist anywhere in the cosmos yet.
No, they had literally never been forged. The timeline of that early chemistry is really fascinating. During the first 3 minutes after the Big Bang, the universe was essentially an unfathomably hot, dense nuclear reactor.
Just protons and neutrons slamming into each other.
Exactly, fusing to create the first atomic nuclei. But the universe was expanding and cooling so rapidly that this cosmic reactor shut down incredibly fast.
So the window just closed.
Slam shut. By the time the universe was cool enough for stable atoms to form, that brief window for nuclear fusion was gone. The final tally was roughly 75% hydrogen, 25% helium, and a tiny, almost negligible trace of lithium. That was the entire periodic table.
Okay, so just to clarify the terminology here, because I know the astrophysics community has a very specific, almost strained way of talking about elements. To a normal person, a metal is something shiny, like gold, silver, iron.
Yeah, but in astronomy, the definition is drastically simplified. A metal is literally any element heavier than helium.
So wait, oxygen is a metal.
Yes. Carbon, nitrogen, neon, silicon, astronomers call all of them metals.
That is so weird.
It's a quirky terminology, sure, but the reason for it is that hydrogen and helium are the primordial building blocks. They're the default state of the universe. Everything else was manufactured later inside the cores of stars.
So when we talk about the environment that birthed these population third stars, we describe it as metal-free.
Right. They were born out of massive collapsing clouds of absolutely pristine gas.
Okay, but if there are no metals, wouldn't the gas cloud just stay a cloud? I'm trying to visualize the mechanics here. Like, how does a cloud of pure hydrogen and helium actually condense into a functioning star? Because I imagine a giant cloud of gas floating in space is going to get incredibly hot as it starts to get squeezed by gravity, and heat wants to expand, right?
You've hit on the central physical crisis of the early universe. The formation of a star is fundamentally a battle between gravity and thermal pressure. Gravity wants to pull all that gas inward, crushing it down into a dense core.
But as you compress gas, it heats up.
Exactly. And that thermal energy creates an outward pressure, fighting the gravity. So in order for gravity to actually win the battle and collapse the cloud into a star, the cloud must have a way to cool down. It has to bleed off that heat into space.
Well, in modern star-forming regions, like, say, the Orion Nebula, how does the gas cool down today?
It uses those heavy elements, the metals we just talked about. Carbon and oxygen atoms are fantastic at radiating away heat. When atoms in a gas cloud collide, they excite the electrons in the carbon and oxygen atoms.
And then what happens?
Well, those electrons quickly drop back down to their normal state, and in the process, they emit a photon, a particle of light. That photon escapes the cloud, carrying away a tiny bit of thermal energy.
Oh, I see.
So trillions upon trillions of these escaping photons effectively act as a cosmic cooling system. Because the gas cloud can efficiently radiate heat away into space, it cools down, loses its internal thermal pressure, and fragments into many smaller clumps.
And those clumps then collapse easily to form relatively small, stable stars like our sun.
Exactly.
So the heavy metals are essentially a car's radiator system. They let the heat escape so the engine doesn't blow itself apart.
That's a perfect way to look at it.
But the primordial clouds in the early universe didn't have radiators. They had no carbon or oxygen.
Right, pure hydrogen and helium are terrible at cooling down at the temperatures required for star formation. Their atomic structures just don't allow them to emit photons efficiently under those specific conditions.
So you basically have a massive cloud of gas being pulled inward by gravity, heating up fiercely, and it has absolutely no way to vent that heat.
None. The thermal pressure pushing outward becomes immense.
So if the cloud is basically an engine running incredibly hot with no radiator, the only way to keep it from blowing apart is to build the engine block out of thicker, heavier, massive amounts of steel. And in this cosmic scenario, that steel is sheer gravitational force.
That is a brilliant analogy. To overcome that immense trapped thermal pressure, gravity had to win through brute force. A small clump of primordial gas simply didn't have enough gravitational pull to crush itself into a star.
It just couldn't overcome the heat.
Right. The cloud had to accumulate a staggering, almost incomprehensible amount of mass before the inward pull of gravity could finally overpower the outward push of the trapped heat. The result was inevitable. The stars that formed from these clouds had to be extremely massive. We are talking about stellar behemoths.
And because they were so massive, the pressure at their cores must have been off the charts,
Oh.
which I'm guessing dictates how they burn.
The core temperatures and pressures were unfathomably high. And here's the brutal irony of stellar physics. You might assume that a massive star, having collected so much fuel, would live a very long time. Like, it has a massive gas tank, right?
Yeah, you'd think it would burn for eons.
But because gravity is squeezing that core so intensely, the nuclear fusion reactions happen at a furious runaway pace. It's literally a cosmic bonfire burning out of control. While a smaller star, like our sun, sips its fuel and will happily burn for about 10 billion years, these massive population third stars just guzzle their hydrogen.
Wow.
They burn through their entire fuel supply in just a few million years. On a cosmological timescale, a few million years is a mere blip. It's the blink of an eye.
So they lived on fast forward. But what happens when that massive gas tank hits empty? Because a star that huge doesn't just quietly fade away or puff out its outer layers.
Oh, no. The end of a population third star's life was among the most violent events since the Big Bang itself. When the hydrogen and helium fuel in the core finally runs out, the outward pressure generated by nuclear fusion suddenly stops.
Just instantly.
Basically. And in that instant, gravity, which has been waiting patiently for millions of years, takes over completely. The entire immense mass of the star collapses inward in a fraction of a second.
That is terrifying.
The core is crushed to an unimaginable density, temperatures spike into the billions of degrees, and the star violently rebounds in a colossal explosion.
A supernova.
Yes. But given the sheer mass of these stars, we are talking about a completely different scale of explosion. Astrophysicists believe many of these stars ended their lives in what is called a pair instability supernova.
Okay, what does that mean?
It's a catastrophic event where the core becomes so incredibly hot that the high-energy photons, so the light itself, actually spontaneously convert into pairs of matter and antimatter particles, specifically electrons and positrons.
Oh, wait. The light inside the star gets so intense it literally turns into solid matter and antimatter.
Yeah, it's the energy mass equivalence, E equals mc squared, in spectacular action. But here's the thing. Photons exert pressure. Particles do not exert the same kind of pressure.
Oh, I see where this is going.
So the moment the light turns into matter and antimatter, the internal pressure holding the star up suddenly plummets. It's like pulling the supporting pillars out from under a skyscraper.
It just falls.
The star experiences a catastrophic collapse, triggering a runaway thermonuclear explosion that completely obliterates the star. There is no black hole left behind, no neutron star. The entire star is blown apart into the surrounding universe.
And that explosion is the crucial mechanism for the rest of the universe's history. Because during their short, furious lives, inside those blistering cores, these population third stars were doing something unprecedented. Right?
Yeah, exactly. They were taking that pure hydrogen and helium and fusing it into heavier elements. They were forging the first carbon, the first oxygen, the first silicon, the first iron. And when they detonated, they blasted all of those newly forged elements outward.
They polluted the pristine universe.
Yes. They seeded the surrounding clouds of hydrogen and helium with those crucial heavy elements. And that changed the mechanics of the cosmos forever. The gas clouds that formed in the aftermath of these explosions now had those radiators.
They had the carbon and oxygen needed to cool down efficiently.
Right, which meant those subsequent clouds could fragment, allowing for the formation of the smaller, longer-lived stars we see today, the population II and population I stars.
You know, think about this next time you drink a glass of water. It's a wild thought experiment. The hydrogen atoms in that glass of water are 13.8 billion years old. They were forged in the chaotic aftermath of the Big Bang itself.
Yeah, it's amazing to think about.
But the oxygen atom, they're bonded to. That oxygen didn't exist at the beginning of time. It was forged in the explosive death of a population third star. When you take a sip of water, you are basically consuming a mixture of the beginning of time and the catastrophic death of a primordial giant.
It's deeply poetic.
Right. Every atom of calcium in your bones, the iron carrying oxygen in your blood, was exclusively made possible because these massive first stars lived fast and died spectacularly.
Without population third stars acting as the universe's first foundries, planets like Earth could never have formed. The chemistry required for biology would be totally impossible. The universe would have remained just a sterile, monotonous expanse of hydrogen and helium gas forever.
So finding evidence of these stars isn't just about filling in a blank spot in an astronomical textbook.
Not at all. It's confirming the very first link in the chain of cosmic events that ultimately led to biological life.
I mean, I understand the theory, and the stakes obviously couldn't be higher. But moving from theory to observation presents an obvious physical problem. If these stars lived incredibly short lives and blew themselves to pieces 13 billion years ago, how do we actually find them? We can't just go looking for their ashes. We want to see the stars themselves.
Well, the only way to see a star that lived and died 13 billion years ago is to look 13 billion light years away. Because light takes time to travel through space, telescopes act as literal time machines.
Right. The further away we look, the further back in time we see.
Exactly. If we look deep enough into the cosmos, we aren't seeing the universe as it is today. We are seeing it as it was when that light first began its journey. So to find population third stars, we have to look incredibly far away, targeting an era when the universe was only a few 100 million years old. We have to catch them while they are still actively forming and burning.
Which brings us to the physical location of this major discovery, because we're zooming in on a very specific cosmic neighborhood. It involves a galaxy known as GNZ11. Now, in the world of astrophysics, GNZ11 is already kind of famous, isn't it?
Oh, absolutely. It's one of the most distant, oldest, and brightest known galaxies in the very early universe.
But the focus of this breakthrough isn't the galaxy itself. It's a faint, seemingly insignificant companion object located right next to it, which astronomers called Hebe.
Right, Hebe. It's situated in what we call the halo of the galaxy. It's located just 3 kiloparsecs away from the luminous core of GNZ11.
Okay, 3 kiloparsecs. Let's translate the spatial geography for a second. A kiloparsec is about 3,260 light years. So 3 kiloparsecs is roughly 10,000 light years away. To a human walking on Earth, 10,000 light years is a vast, unimaginable distance. But on a cosmic scale, if we look at massive structures like galaxies, is Hebe basically just sitting in the immediate suburbs of GNZ11?
Oh, yeah. 3 kiloparsecs is practically right next door in galactic terms. To give you some spatial context, the bright disk of our own Milky Way galaxy is roughly 100,000 light years across. So Hebe is sitting well within the gravitational sphere of influence, the halo of GNZ11. It's deeply entwined with the galaxy's environment.
But wait, that raises a massive observational red flag for me. If Hebe is that close to one of the brightest galaxies in the early universe, shouldn't the sheer blinding brightness of GNZ11 completely wash out our ability to see a tiny, faint companion? It sounds like trying to spot a firefly fluttering right next to a military-grade searchlight. I mean, the glare alone should make it invisible.
The glare is an astronomical nightmare, you're right. Telescopes suffer from diffraction, which is the way light bends and scatters when it enters the optics. A brilliantly bright object like GNZ11 will naturally spill light into the surrounding pixels on a detector, potentially drowning out anything faint nearby.
So how do we even see it?
Well, overcoming that glare requires incredible optical precision and sophisticated data processing to subtract the light of the host galaxy and isolate the faint signal of the companion. But what's fascinating here is that proximity, the very thing making it difficult to observe, is also exactly why Hebe is the key to this whole mystery.
Wait, how does being next to a blazing galaxy actually help the situation?
Yeah.
If GNZ11 is so active, shouldn't it have already polluted its suburbs with heavy metals?
The timeline of cosmic pollution is the critical factor here. Remember, we are observing this system as it existed just 400 million years after the Big Bang. GNZ11 is indeed a bustling, intensely luminous galaxy experiencing a massive burst of star formation.
So there's supernovae happening there.
Constantly. The stars in its dense core are living, dying, and exploding, which means the very center of GNZ11 is already becoming enriched with heavier elements. The core is polluted, but the universe is still incredibly young. The vast space surrounding the galaxy, the extended halo, hasn't been completely mixed yet. The supernova winds haven't had enough time to push those heavy elements out to a distance of 3 kiloparsecs.
So the smog hasn't reached the suburbs.
Precisely. The fact that Hebe is sitting on the outskirts means it is still a pristine, uncontaminated pocket of primordial gas. It is a massive cloud of pure hydrogen and helium. Finding an uncontaminated area is rare enough, but finding one so close to a bright, intensely active galaxy is what makes Hebe the perfect laboratory.
Because the intense radiation pouring out of GNZ11 is essentially acting as a massive backlight. It's illuminating this pristine gas cloud, giving us a clear view of it without physically dumping heavy metals into it.
Exactly. It provides the energetic context to make the cloud visible. And because the chemical makeup of Hebe is still pure, it's the exact type of raw, unpolluted environment where the massive, metal-free population thirst stars can still actively form.
Okay, so we have our setting. We're staring deep into the halo of GNZ11, focusing on this tiny, uncontaminated suburb called Hebe, 400 million years after the birth of time. But when astronomers say they observed Hebe, they didn't just get a high-resolution Polaroid picture of a giant star, right? I mean, they can't see the physical shape of a star from 13.4 billion light years away. Everything is just a smudge of light. So what are they actually looking at to determine what's inside that smudge?
You're absolutely right. At these extreme cosmological distances, spatial resolution, the ability to see physical details, is largely impossible for individual stars. Instead of looking at the shape of the light, astronomers analyze the behavior of the light. They rely on spectroscopy.
Breaking the light apart to see what it's made of.
Spectroscopy is arguably the most powerful tool in all of astronomy. Imagine taking the faint light captured from Hebe and passing it through a highly advanced prism, or, more accurately, a complex diffraction grating. This splits the light into its component wavelengths, spreading it out into a spectrum, much like a rainbow.
And why is a rainbow of light useful?
Because of quantum mechanics. Every chemical element in the universe interacts with light in a unique way. An atom of oxygen will absorb and emit light at very specific exact wavelengths. An atom of carbon will do the same at different wavelengths.
So it leaves a mark.
Exactly. When we look at the spectrum of a distant object, we see dark lines where light has been absorbed by certain elements and bright lines where light is being intensely emitted. That spectrum is a literal chemical barcode. By reading the barcode, we don't have to guess what an object is made of. The laws of quantum physics tell us exactly what elements are present in that distant cloud of gas.
Which brings us to the technological marvel that made this discovery possible. In 2024, a team led by Roberto Maialino at the University of Cambridge utilized the James Webb Space Telescope. But they weren't just using the main cameras. They employed a highly specific instrument called NIR-SPEC-IFU, the Near-Infrared Spectrograph Integral Field Unit. I mean, it sounds like something out of a science fiction novel. How does this specific instrument read a barcode from 13 billion light years away?
The NIR-SPEC instrument is honestly an engineering masterpiece. One of its greatest innovations is a microshutter array. It contains roughly 250,000 tiny doors, each about the width of a human hair.
250,000 tiny doors.
Yeah. And astronomers can program these doors to open or close, allowing them to block out the overwhelming glare of a bright object like the host galaxy GNZ11, and only allow the faint light from a specific target like Hebe to enter the spectrograph.
That's incredible.
And once the light enters the integral field unit, it doesn't just take one spectrum. It takes hundreds of spectra simultaneously across the entire spatial area of the target. It creates a 3D data cube mapping not just the chemistry, but where that chemistry is happening within the cloud.
So when Maialino's team pointed this incredible machine at the faint smudge of Hebe and analyzed the 3D data cube, they found a very specific, glaringly obvious anomaly in the barcode. They detected a distinct emission line that corresponds to doubly ionized helium. And just as importantly, they looked for the barcode lines of heavy metals, carbon, oxygen, iron, and found absolutely nothing.
The combination of those two facts is the astrophysical smoking gun.
Okay, here's where it gets really interesting. Let's unpack the physics of doubly ionized helium, because it sounds highly technical, but it's the core of the discovery. Helium, in its standard state, just floating around, is a very stable atom. It has a nucleus with 2 protons, and it's orbited by 2 electrons.
Right. It's the second most common element in the universe, and it takes a lot of energy to disrupt it. If you want to strip one of those electrons away from the atom, a process called ionization, you have to hit the atom with a significant amount of energy, typically high-energy ultraviolet light.
But the barcode from Hebe didn't show standard ionized helium. It showed doubly ionized helium, meaning both electrons have been violently ripped away, leaving the helium nucleus completely bare.
And the energy required to accomplish that is staggering. To strip that second electron away requires photons carrying more than 54.4 electron volts of energy.
Let's contextualize 54.4 electron volts for a moment. If I go to the beach on a hot summer day and I forget to wear a sunscreen, the ultraviolet light from our sun hits my skin and causes a sunburn. It's literally damaging the DNA in my skin cells. How much energy do those UV photons from our sun carry?
The ultraviolet photons causing your sunburn carry roughly 3 or 4 electron volts of energy.
3 or 4 electron volts.
Yeah.
And the light hitting the gas cloud in Hebe is packing 54.4 electron volts. We are talking about radiation so unbelievably intense it would instantly obliterate molecular bonds. What kind of object is capable of generating that level of harsh, extreme ultraviolet radiation?
The source of that light has to be unimaginably hot. The amount of extreme ultraviolet radiation a star emits is directly tied to its surface temperature. To produce a continuous flood of photons packing 54.4 electron volts, the surface temperature of the star has to be well over 80,000, perhaps even 100,000 degrees Kelvin.
The surface of our sun is about 5,800 degrees Kelvin.
Exactly. We are looking at a heat source more than 15 times hotter than the surface of our sun. Even the most massive, hottest blue stars burning in our modern galaxy rarely reach temperatures hot enough to produce a doubly ionized helium signal this strong. Standard stars simply cannot do it. When Maialino's team saw that specific helium line in the data, they knew instantly that whatever was hiding inside the Hebe gas cloud was generating blistering, almost unprecedented levels of heat.
But science requires us to play devil's advocate. Just because we see intense heat doesn't automatically mean we've found a mythical population 3 star. Aren't there other things in the universe that can generate extreme heat? What about, say, an actively feeding supermassive black hole? A quasar. As matter falls into a black hole, it creates an accretion disk that spins incredibly fast, generating immense friction and unbelievable heat. Couldn't a hidden black hole inside Hebe produce the 54.4 electron-volt radiation?
It's a great question, and it's the most rigorous alternative hypothesis. An active galactic nucleus, or a quasar, is entirely capable of generating the extreme ultraviolet radiation necessary to doubly ionize helium. But this is where the second part of the barcode becomes vital. Black holes are messy eaters.
Messy how?
The environments around actively feeding supermassive black holes in the early universe are almost universally characterized by massive, swirling outflows of gas. And crucially, that gas is almost always heavily polluted with metals. The intense friction and energy involved in the accretion process churns up elements.
So if it were a black hole, we would see the metallic smoke. Like if we see a massive heat signature but absolutely no smoke from a campfire, we know something highly unusual is burning.
Exactly. We would see pronounced emission lines for carbon, for oxygen, for nitrogen. But when the JWST scrutinized Hebe's spectrum, the metal lines were conspicuously absent. The noise level on the detector was incredibly low, meaning if metals were there, JWST would have seen them. But the reading was 0. The gas cloud is pristine.
So we have a puzzle. We have a radiation source hot enough to strip helium bare, which suggests a massive violent engine. But we have an environment completely devoid of the heavy elements that normally accompany such violent engines.
And when you eliminate the impossible, whatever remains, no matter how improbable, must be the truth. When you combine a heat source capable of generating 54.4 electron-volt photons with a definitively metal-free gas cloud, the active black hole theory falls apart. There is only one elegant, scientifically sound explanation left standing: a cluster of massive, incredibly hot, pure gas, population-thirst stars. The theoretical giants are the only things that fit both criteria perfectly.
The technological leap required to even have this debate is astonishing. We're casually talking about analyzing the chemical makeup of a gas cloud from 13.4 billion years ago. For decades, the astrophysics community knew what the signature of population-third star should look like, but they simply didn't have the tools to look for it.
Right. Ground-based telescopes were largely useless for this specific search because the Earth's atmosphere absorbs and distorts large portions of the infrared spectrum. And even our most advanced orbital observatories, like the Hubble Space Telescope, were fundamentally ill-equipped. Hubble was designed to see primarily invisible and ultraviolet light.
Wait, but why does visible light fail us when looking at the early universe?
Yeah.
If the stars were emitting ultraviolet light, shouldn't we be looking for ultraviolet light?
This is where the expansion of the universe plays a critical role. Space itself is stretching. As the blistering ultraviolet light from Hebe began its journey 13.4 billion years ago, it was indeed high-energy UV light. But as it traveled, the fabric of space expanded beneath it. This expansion literally stretched the wavelength of the light.
Oh, like a redshift.
Yes, it's a cosmic version of the Doppler effect. Think of a police siren dropping in pitch. As it speeds away from you, the sound waves are being stretched. In space, the light waves are stretched, shifting them from the tight, energetic ultraviolet down through the visible rainbow and deep into the infrared spectrum. This phenomenon is called cosmological redshift.
So the ancient ultraviolet light is now invisible infrared light.
By the time the light from Hebe reaches Earth, its wavelength has been stretched by a factor of 11. It has shifted entirely out of the visible spectrum. The James Webb Space Telescope was explicitly engineered to solve this problem. It was built with a massive, gold-plated beryllium mirror to capture as much faint light as possible, and it is optimized to see exclusively in the infrared.
That's brilliant.
The NIR-spec instrument didn't just take a photograph. It caught light that had been traveling since the dawn of time, untangled its stretched-out wavelengths, and revealed its fundamental chemical DNA. In a single observation window, the JWST shifted this entire field of study from a chalkboard exercise into an observable reality.
But, the scientific community is notoriously, and rightfully, skeptical. Seeing something incredible once is a tantalizing hint. It might get you a headline. But seeing it twice, from different angles, using different methodologies, that is a confirmation. When you are dealing with signals this faint, captured by a machine floating 1,000,000 miles away in space, how do we know this delicate helium signal isn't just a glitch? A cosmic ray hitting the detector at the wrong moment, or an artifact in the data processing software?
The fear of false positives is a huge driving force in astronomy. We've seen premature announcements before. The astronomers involved understood the gravity of their claim. They knew they couldn't just publish one paper based on a single observation and declare the mystery of population 3 stars solved. The data had to be brutally tested.
So what did they do?
Well, Roberto Maiolino's team didn't rest on their laurels. They immediately followed up their initial detection. They utilized the high-resolution grading on the NAR-SPEC instrument to take a much closer, much sharper look at the helium spectrum.
They basically swapped the magnifying glass for a high-powered microscope.
Exactly. They needed to see the fine structure of the light, and the high-resolution data provided spectacular validation. Not only did it confirm that the doubly ionized helium signal was undeniably real, it actually resolved the signal into two distinct components. It showed variations in the wavelength that allowed them to map the kinematics, the actual physical movement of the gas within the Hebe cloud.
So it wasn't a glitch.
No, the signal wasn't a static glitch at all. It was a dynamic, moving, physical system, but the most profound validation didn't come from Cambridge. It came simultaneously from a completely different set of researchers.
Enter the second team. While Maiolino's team was obsessively scrutinizing the helium data, an entirely independent study was being conducted by a team led by Elka Rusta at the University of Florence. They were looking at the exact same public JWST data release, staring at the exact same coordinates in the halo of GN's 11, but they weren't looking for helium. They were hunting for something else.
They were searching for hydrogen, specifically a very distinct emission line known as the Balmer alpha or H-alpha line.
Wait, finding hydrogen sounds kind of easy, doesn't it? I mean, it's everywhere.
Finding hydrogen in the early universe might sound trivial since it makes up 75% of the cosmos. But isolating the specific emission signature of a single highly energized cloud at a redshift of 10.6 is incredibly difficult. It requires meticulous data subtraction and a deep understanding of how the surrounding intergalactic medium absorbs light.
But Russ's team successfully detected the distinct hydrogen emission line, and crucially, they pinpointed its origin to the exact same physical location as the helium anomaly. So we have two separate teams acting almost like cosmic detectives, working different angles of the same case. One team isolates the anomalous helium. The other team isolates the primordial hydrogen.
Yes. And the most important part of this independent verification isn't just what they found, it's what they both failed to find.
The missing metals.
Exactly. Neither study, despite using incredibly sensitive analysis techniques, found any trace of heavier elements. They both confirmed the total absence of metals. In the logic of scientific discovery, the lack of metals is the dog that didn't bark in the night. It's the crucial piece of missing evidence that solves the case.
It's huge.
Elka Rusta's independent detection of the hydrogen line provides a vital second anchor for the physical reality of the object. If only one team had reported a weird blip, the community might remain skeptical. But when you have two distinct analyses confirming the presence of intensely energized foundational elements, hydrogen and helium, in the exact same spot, while simultaneously confirming a completely pristine zero-metal environment, the conclusion becomes practically unassailable.
It completely rules out the glitch theory. A software error isn't going to artificially create a perfect hydrogen line and a perfect helium line while simultaneously scrubbing all the metal lines.
It demonstrates the scientific method operating flawlessly at the highest levels of observational complexity. Independent teams utilizing distinct analytical pipelines, converging on a single, unified physical truth. Hebe is a pristine pocket of primordial gas, and it is being bombarded by extreme radiation from within. The theoretical ghosts have finally cast a physical shadow we can measure.
We know they are there, the verification is solid. The next logical question immediately demands an answer. Just how massive are these stars? We've been calling them giants, behemoths, stellar titans. But in physics, we need numbers. So what does massive mean in this specific context? And this is where the genius of Elka Rusta's team really elevates the research, because their focus on the hydrogen line provided the exact tool needed to weigh these ancient stars.
Finding the hydrogen emission wasn't just a geographical cross-check. It unlocked a powerful new diagnostic capability, a mathematical ratio. Because astronomers now possessed precise, verified measurements for the intensity of both the hydrogen emissions and the doubly ionized helium emissions, Rusta's team could calculate the exact observed helium-to-hydrogen ratio within the Hebe cloud.
Okay, wait. How does comparing the brightness of two glowing gases tell us the physical weight of the stars hidden inside the cloud?
It relies on the strict laws of stellar physics. The amount of doubly ionized helium you observe in a gas cloud depends entirely on the volume of extreme 54.4 electron-volt radiation hitting it. The cloud is just a reactive canvas. The star is the projector. And the amount of that extreme radiation a star produces is fiercely mathematically dictated by its mass.
Because more mass means a stronger gravitational crush, which creates a denser, hotter core, which drives a hotter surface temperature, which results in a flood of harsher ultraviolet light. So the weight of the star directly controls the temperature of the light.
Exactly. The relationship is highly predictable. By taking the exact observed ratio of helium to hydrogen from the JWST data, Rusta's team could run the cosmological clock backward. They fed this specific light ratio into highly advanced theoretical models of stellar evolution and atmospheric physics. They essentially asked the computer, in order to produce exactly this ratio of glowing gas, what must the mass profile of the stars hidden inside this cloud look like?
They reverse engineered the light to find the engine. What did the analysis reveal about their size?
It revealed a remarkably top-heavy mass distribution. The models clearly indicated that the vast majority of the population, the third stars forming inside Hebe, had to be incredibly massive, with most of them falling somewhere between 10 and 100 times the mass of our own sun.
So what does this all mean? 10 to 100 times the mass of our sun. That is a staggering scale. To put that in perspective, our sun accounts for 99.8% of all the mass in our entire solar system. You could fit 1 million Earths inside of it. And these primordial stars are 10 to 100 times more massive than that. So if our sun is a standard sedan, these stars are an entire fleet of massive commercial dump trucks. But what is really fascinating is the phrase you used, top-heavy mass distribution. How does that compare to the stars forming in our galaxy right now?
It's the exact opposite of modern star formation. In a galaxy like the Milky Way, star formation is governed by what we call the initial mass function, and it is extremely bottom-heavy. When a modern gas cloud collapses, it produces a vast swarm of very small, cool stars called red dwarfs. It produces a handful of medium-sized stars like our sun, and it only produces a tiny, exceedingly rare fraction of massive, hot blue stars.
So giant stars are the ultimate cosmic rarity today.
Right. But in the early universe, inside pristine clouds like Hebe, the physical rules were inverted. The environment preferentially birthed giants. The top-heavy distribution means that massive 50 solar mass behemoths weren't the exception, they were the rule.
Finding that specific mass range, 10 to 100 solar masses, must have sent shockwaves through the theoretical physics community. For decades, theorists have been sitting at chalkboards calculating the thermodynamics of metal-free gas clouds and insisting that the universe's first stars had to be huge to overcome thermal pressure. The math demanded it. But as we know, math isn't proof until observation confirms it.
It is an incredible triumph for theoretical astrophysics to finally have raw empirical data beamed back from the JWST and to have the analysis of that data yield a mass range that perfectly aligns with decades of theoretical predictions. It's a profound validation. It proves that our fundamental understanding of how gravity, thermodynamics, and quantum mechanics operate in a primordial alien environment is fundamentally correct.
It's like digging up a building.
Yes. It's one thing to draw the architectural blueprint of a building that existed 13 billion years ago. It's an entirely different level of satisfaction to finally dig up the foundation and find that the stones match the blueprint perfectly.
This confirmation doesn't just put a neat bow on a single astronomical mystery, does it? It forces us to re-examine the structural evolution of the entire universe. If the early cosmos was populated by a massive generation of 100 solar mass stars burning fiercely and dying quickly, what does that mean for everything that came after?
The implications are vast, particularly concerning the formation of black holes. When a 100 solar mass star dies, if it doesn't completely obliterate itself in a pair instability supernova, its core collapses into a black hole. A top-heavy generation of population third stars would have left behind a massive swarm of heavy seed black holes.
Well, that's a big deal because
astrophysicists have long struggled to explain how the supermassive black holes at the centers of galaxies grew so large so quickly in the early universe. These population third giants might be the crucial seeds that merged and grew into the cosmic leviathans that anchor galaxies today.
while astronomers certainly need more time on the JWST to fully map the distribution and the life cycles of these ancient stars across different pockets of the early universe, these independent, verified results from the Mayalino and Rusta teams represent a paradigm shift. We are no longer guessing. We are finally standing on solid observational ground when looking back 13.4 billion years.
We really are. We're transitioning from educated speculation to rigorous empirical science regarding the origins of the structures that shape our entire universe today. These early massive stars were the great engines of transformation. They forged the first heavy elements. Their intense ultraviolet radiation helped strip the electrons back off the neutral hydrogen gas that filled the early universe, lifting a cosmic fog and allowing light to travel freely through space. They violently engineered the cosmos into a state where galaxies, planets, and eventually complex chemistry could exist.
Let's take a moment to look at the incredible intellectual and technological journey we've just navigated. We have essentially traveled 13.4 billion light-years across the expanse of expanding space, peering into an era just 400 million years after the birth of time. We navigated the blinding glare of the early galaxy GNZ11, zeroing in on a tiny, uncontaminated pocket of gas named Hebe. By capturing the stretched-out invisible light of the cosmos and decoding the ancient signatures of doubly ionized helium and hydrogen while proving the absolute absence of any metallic pollution, two independent teams of scientists have finally illuminated the ghosts of the cosmos.
They have uncovered the fingerprints of the population third stars. Those colossal pure gas giants that lived brilliantly, burned fiercely, and died violently in massive supernovae, all to seed the sterile universe with the very first heavy elements, the fundamental building blocks of planets and the building blocks of biology.
Understanding the mechanics of a 100 solar mass star isn't just an exercise in balancing a cosmological ledger or cataloging ancient space anomalies. It is a profoundly intimate realization. It's about tracing your own physical lineage. When you look at your hand, when you take a breath of air, you are actively utilizing elements that were forged in the furious, crushing crucible of these exact stars. You are tracing your story back to the very first light that ever pierced the dark. Which leaves me with one final, provocative thought to consider. Well, the universe has clearly been hiding its most ancient, profound origins in plain sight, just waiting for human engineering and ingenuity to catch up. For over half a century, population 3 stars were just a math equation. Today, they are an observable reality. If a machine floating 1 million miles from Earth can now see the theoretical first stars born from primordial gas, what other hypothetical cosmic phenomena are currently lingering in the dark? What other impossible structures are floating out there in the abyss, just waiting for the right telescope, the right instrument, to turn them from a mathematical theory into a profound, undeniable reality? The next time you find yourself far from the city lights, standing in the cold, and you look up to trace the starlight back in time, just remember, the dark isn't empty. It's just waiting for us to see it.